a recurring theme has been how do we kind of prevent context poisoning. I think Vanya earlier on in the day said something about how do we make sure that if an AI essentially gets context and information which are kind of in conflict with each other, how do we kind of prevent it from going off the rails, right? So one of the things that I kind of want to restrict myself in this situation is to talk about how do we actually build traceable reasoning when trying to do legacy modernization. More importantly, how do we specifically do reverse engineering? And when we do reverse engineering, as Thiago was talking about in the last talk, one of the chief issues is AI potentially hallucinating on what it thinks the actual functionality is. So how do we ground some of those conclusions that AI comes up with? What are the different things around facts and notes at looking at the legacy code itself, which will kind of help us trace whatever we assert with whatever is actually present in the legacy code. So that kind of is sort of like the scope of this talk. I'm going to skip the thing about me because I think they've already kind of talked about that. So just kind of surveying very quickly in terms of the sorts of materials that we have to work with when we are kind of trying to do reverse engineering. There's a whole bunch of different stuff, right? So, we have already seen things like screenshots with user inputs. We have seen like recorded input data. We have seen things like initial database state. These are things that you can observe without essentially kind of getting your hands dirty inside the system itself. What are the sorts of outputs that you can essentially observe? You can look at similarly like screenshots, right? Like outputs which are kind of coming out. You can look at the final database state. You can look at the output logs and so on and so forth. Those are the things which you could very loosely kind of classify as like artifacts which help us in black box reverse engineering. However, there's always another set of artifacts which is essentially the code itself, whether it is the actual static artifacts, when we're talking of whether it's code, whether it's configuration, or whether it's like things like like the database itself. This can actually be the static artifacts, or these can actually be the code which is actually running in a deployed system itself. So there's a whole bunch of different ways in which you can actually do reverse engineering, and all the talks have kind of attested to that. I will kind of focus more specifically around white box engineering, which is the case where you do have access to some of the artifacts, which include the code, configuration, and so on. And my thesis in this case is that to actually do reliable white box engineering, there are essentially three pillars. What are these three pillars? The first pillar is structural analysis. To most of us, code, and even to the computer, code is essentially just a bunch of text files, right? However, before any code is run, there is always a set of processes, whether it's a compiler, whether it's an interpreter, whatever it is, which essentially extracts a lot of hidden structure which is present in the code, which makes it suitable for ultimate execution by your CPU. So that's where you want to kind of mine the hidden structure which is kind of available in your code. What these hidden structures are is something that we'll come to in a second. The second thing is, as I already kind of talked about, is traceable reasoning, which is that every conclusion that is drawn from the analysis of legacy code can be rigorously traced back to the actual source to ensure the verifiability and trust. And finally, a world model. So what do you mean by a world model? You might be looking at a piece of code and you might be saying, hey, there is this variable which might be holding the value of a user's stacks. That might be your initial hypothesis. However, when you uncover more facts about the code base, you might revise your opinion and say that, you know what, this variable, I thought this was holding tax, but it's not. It's probably kind of, like holding just the price of an item or something. Which means that, as humans, when we kind of try to understand code itself, our assumptions do not remain static. So the term non-monotonic is kind of borrowed from logic programming, which says that once there is a fact which you have, say, for example, deduced from looking at your observations, it does not hold that that fact is going to stay true after you gather more information, which means that a fact which is true today can essentially kind of become false or change tomorrow. That's what it means in terms of a non-monotonic world model. So let's talk a little bit about structural analysis. And the reason I'm going to be talking of structural analysis in this case, this is going to be more around like, like computer science related rather than specifically AI related. But if you just kind of hold your patience for a bit, we'll see how it essentially kind of ties to the sorts of things that an AI could essentially use. So, if you have kind of, delved a little bit into how, when you write some piece of code, how it essentially kind of gets translated to ultimately be executed inside a CPU, you might know that ultimately a code, any piece of code that you write, ultimately gets translated into different representations. And the most usual representations are essentially graph representations. The most popular kind of graph, popular and the default graph representation is abstract syntax tree. And I'll just skip for a second to show you what an abstract syntax tree essentially looks like. So here's an example of a while loop. The abstract syntax tree essentially kind of breaks it out into multiple tokens which are organized hierarchically to reflect the actual structure of the code. So the top level would essentially be a node which essentially represents the while loop, right? And then, inside that, it essentially has a bunch of children. One of the children is essentially your comparison of b not equal to 0 and so on and so forth. So it essentially kind of breaks it down because a compiler to actually execute this program or like compile it into machine code, it obviously does not understand English. It needs to understand the structure, and this structure is the first step towards getting to that executable representation. The second kind of graphs that we usually deal with are control flow graphs. Very simply, control flow graphs are nothing more than flowcharts. So here is an example of a control flow graph. So on the right side, you are essentially seeing what it would look like if it were kind of formatted for human readability. On the left side, you are essentially seeing a control flow graph, essentially the same thing, but represented as a graph without all the pretty formatting and so on. This is essentially for a 4,000, 5,000 line program. So as you can see, control flow graphs can be really big. Now the question is, why should we really care about all of these things, right? So, there are a couple of other structures that we have that I've listed down, and I'll come to those while we kind of talk about. The question is, what is the point of talking about these? Why am I talking about these in the context of legacy modernization? Why am I talking in the context of AI? Because these representations are actually representative of facts about the program. For example, if you have a control flow graph, you know which function essentially calls which other function. If, say, for example, if you have a dominator tree, which I'll kind of talk about in a second, even if, say, for example, you are working on a legacy stack like, say, COBOL or machine code, which might not, say, for example, use structured programming constructs. They might have gotos and other sorts of unstructured programming constructs. You can actually recover many of those hidden details, which a human would be kind of like, would have to do quite a bit of analysis to uncover. But these different kinds of representations kind of uncover different aspects of the program. In fact, each of these type of graphs is optimized to make explicit some particular desirable property of the code in question. What do I mean by that, right? I'll come back to this in a second. So let me just jump ahead to kind of talk a little bit about this example. So look at the graph, which is completely on the left, right? It's basically just, I think, like 5 nodes, A, B, C, D, E, and so on. I want to play a game. The rules, there are only 2 rules. One is, if there is a node which has a loop to itself, I get rid of the loop, right? Simple enough, right? The second thing is, if there are 2 nodes connected to each other, say, for example, A and B has only one incoming edge to it, I basically merge A and B. Does that make sense? So those are the only 2 rules. So the thing is, for B, if there are 2 incoming edges into B, I cannot merge A and B. There has to be only one incoming edge for A and B to essentially be merged. So these are the only 2 rules that I kind of want to do to kind of play this game. What I'll do is I apply these rules repeatedly to the graph on the left. So what essentially happens is the first graph on the left, B and C essentially merge, D and E essentially merge, and then B, C, D, E merge, and then finally everything kind of collapses out into one node which kind of contains the entirety of A, B, C, D, E. Now, why am I playing this game? In fact, if you look at it in software engineering, if you consider each of these nodes to actually be computer instructions, it doesn't matter whether they're machine code, whether they are like high-level JavaScript or C or whatever it is. The point is, this kind of a graph, if you can essentially reduce it to a single node, it's called a reducible graph. And this is very strongly correlated by how well structured a program is. What do I mean by a well-structured program? A well-structured program is something that can be easily represented by just your normal programming constructs, like while, for, break, continue. Now, how is this different from an unstructured program? So here's an example of an unstructured program. It's exactly the same graph. The only difference is, in addition, on the graph on the leftmost side, there is an edge from A to C. And if you can see, if you try to apply those same two rules, you cannot reduce this to a single node. You can try this example later on just to kind of prove to yourself that this works. What this means is, if this were a computer program, it essentially means that there is an instruction from A which essentially jumps directly into the middle of a loop. Almost like if you have a goto. So if you have a goto just jumping around randomly, you cannot essentially easily convert that kind of a program into a well-structured program, the kinds of programs and languages that we usually kind of write in. So these sorts of tests, like these are like graph theory sort of techniques. These kind of give us a sense, if you're looking at a legacy piece of code, and you're looking at a program and you want to know whether this is a well-structured program, whether it can be translated easily enough, or whether the logic is convoluted because of a lot of random go-tos jumping around everywhere. This sort of test can essentially kind of give you a strong indication of the complexity of the program or how tangled the program is. In fact, you can actually use the same technique even on code that you are currently writing and maintaining itself. It's just that ultimately legacy code is obviously more prone to unstructured, these sorts of unstructured patterns and stuff. This is an example of how a control flow graph can kind of give you extra information. Here's another thing that you can do. Suppose you are looking at a program, right? You are looking at an assembly piece of code. Assembly code, right? There are no loops. There is no for. There's no while. However, loops might be implemented using jumps and so on and so forth, right? What you can do is you can do a kind of analysis which is called dominator analysis. So here is an example of a loop which is like B, C, D, right? So like B, C, D, and back to B. Looking at it directly, yes, it's a loop because it's a very simple, this is a very simple graph. However, if this is a very large program with massive like loops within loops and so on and so forth, it would be difficult to kind of do this sort of analysis manually. However, if you can do this sort of this is an automated technique, where it basically says that every path to C and D has to go through B. You cannot go to C without ever going to B, which means that in graph theoretic terms, B dominates C, B dominates D. And anything which essentially dominates other nodes essentially becomes the start of a loop. That is a theoretical result which you can essentially apply to anything. Compare that to the example on the right side where you can get to C without going through B because you can just take directly a shortcut from A, which means that B is not a dominator, which means that BCD, even though it might actually look like a loop, just to a normal human eye, it's not actually a loop in computer science terms, which means you can't directly translate this into a well-structured program as well, right? So let me just go back really quickly, right? So we have kind of talked really quickly about structural analysis. The other important thing is when you are kind of looking at any sort of piece of code, one of the important things is you want to be able to extract out the structure. However, legacy code always sometimes, and in many cases, has errors. A legacy code might necessarily have like missing pieces of a code, or it might have been not run for so long that it might actually have like syntax errors and so on and so forth. In all these cases, to actually extract out the structure, normally, if you write a program and it has a syntax error, your compiler stops immediately, right? However, in legacy code, we don't really have a choice. We have to kind of get out the structure, right? Like our clients are kind of like paying us money for it. So in this situation, when you're kind of like trying to like do some sort of parsing to be able to extract out the structure, you need to be prepared to be able to work with noise. You need to be prepared to kind of work with ambiguous code or code which is not clean enough. So this is an example of this is also assembly language, which is also, I think, what the previous speakers spoke about. But this is a mainframe assembly language. This is not x86 assembly language. This is an example of an assembly language where it can be embedded inside COBOL, as well as you can actually embed actual directly like SQL statements from inside there itself. So here is another example of how you can essentially do multi-pass parsing, where you kind of extract out, in each pass, you extract out different features of the code. In one place, you kind of parse your HLASM, which is basically your high-level assembly language. In another parse, you kind of parse out your DB2. And then, of course, you keep on sanitizing code. So the point is, these are processes that you would probably want to do in order to be able to kind of extract out the structure, even when the actual code is not ideal, right? So let me just move over. We have talked quite a little bit about the different kinds of structure. I'm going to move over really quickly. So these are all similar things around like reducibility. Another point to know about reducibility is that another point to know about reducibility is after performing your reducibility, if you get down to a region which is not reducible, it means that there are multiple edges coming into it, right? Which means that there are multiple pieces of code calling that specific piece of code, which also is a strong indicator that that piece of code might be a very shared piece of code, which would be good for refactoring. It might potentially be ending up in a common library, or it might be a very often used part of the program itself. So that's another example of how using reducibility can kind of give you hints about the program structure, even if you know nothing about the program logic, even if you know nothing about the actual domain logic itself. The last technique that I'll kind of talk about is symbolic execution. It's kind of like in a weird hybrid of actual execution, but not actually executing. So the idea is, suppose you have a statement, right? A is equal to b plus 1, right? Now, if I were to kind of ask you, what is the value of a? You would not be able to tell me the value of a unless you knew the value of b, right? So, only if you knew that value of b was equal to 2 or something, then you could say a is equal to 2 plus 1, which basically becomes equal to 3. Symbolic execution basically says that, you know what, I don't really need to care about the exact values of our variables. If I'm running a program and all I do is all the initial values of the variables are not actually like actual numbers or strings or whatever, but they're just symbols, right? So if they are symbols, then what I need to do is every time I'm kind of using a variable, whether I'm adding to that variable or I'm subtracting to a variable, I just kind of keep on accumulating the computation. So here is an example. This is an example of a toy virtual machine that I wrote to kind of explain this concept. This is kind of like a very simple assembly language, a fictitious assembly language. This one, it essentially has like two registers in this case, R1 and R2. And R1 and R2 initially kind of start off with symbols. They are not actually assigned to like actual numbers. Now what happens is when I actually run this code, what happens is at the end of it, you will see that the final result, R1 will basically be C. R2 will actually be equal to INCB, which means it's the same thing as saying R2 is equal to B plus 1, where B was the original symbol. So ultimately, what you are kind of doing is you are still executing the program technically, but the final result is not concrete numbers. It's not concrete values. It's almost like you are solving an algebraic equation, right? You ultimately express the final values that your variables assume in terms of symbols, not the actual concrete variables. And this is an example of how you can kind of execute multiple snippets of code without really worrying about what the actual computation inside is going on, because ultimately at the end, the values of those variables will essentially be expressed as some computation of all of these symbols. So this is another way in which you can kind of extract out the logic without actually executing the program in its actual environment, while still, kind of getting the benefits of, in some sense, kind of like running the program. So let's shift a little bit. So far, we have kind of been talking about the facts, right? Like these are facts which have been extracted out of the program. Yeah, function A calls function B. This variable is expressed in terms of the other variable, and so on and so forth. But that's not what I guess we are trying to modernize, right? We are kind of trying to ultimately understand what the actual logic is, right? Like what is the business logic? It would not be very helpful if we were only to say that, hey, this variable means this. That is not enough. Usually we want to extract out domain logic, right? And in this case, what we usually kind of end up doing is obviously use LLMs. But one of the important things is LLMs can kind of give you a result very confidently, and you might be left in the dark saying, okay, is this true or is this false, right? So one way in which we can kind of keep evolving our belief and kind of quantify whether an LLM is saying something, whether it is true or false, or whether it's partially true or partially false, is something that us as humans kind of do every day. And it's a class of reasoning called Bayesian reasoning. So just to take an example, right? You see a pavement which is wet one day. You might have two hypotheses, right? One hypothesis might be the sprinkler was turned on. Another hypothesis might be it rained the previous day. Both of those initially are equally likely. But say, for example, you go and read the newspaper, the weather report, and it says that it had actually rained earlier that day. Which hypothesis do you think will become stronger in your mind? The fact that it had rained, right? So which means you had a prior belief about a hypothesis. Say, for example, if it was rain. You did an observation, the observation being you looked at the newspaper report, you saw an observation, and then you updated your internal belief about that specific hypothesis. And this is, in some sense, a cycle, right? I mean, this is also kind of allows us as humans to kind of keep conflicting beliefs about different things in their mind. Like, say, for example, if you are like a detective or something, right? You're trying to solve a murder. You might have like 20 hypotheses. You might have 5 hypotheses, right? Like, how did this person die or something? Now, in an LLM might say, for example, narrow down and pick one of those hypotheses and say, this is what it is. But humans, we have the ability to kind of keep different levels of belief in each of these hypotheses, then based on evidence, kind of either strengthen or weaken some of these hypotheses, and finally come to some probable cause based on whichever hypothesis kind of won out the strongest. So here's an example that I did. How do we validate a hypothesis using an LLM, right? So this is a single hypothesis, right? The example hypothesis that I used is I just took a very simplistic program, right? And I said, hey, I want to validate the hypothesis that this program uses a lot of registers, basically a lot of variables, right? And what I do is I don't, kind of just give the LLM, just let the LLM kind of guess. What I really did is I kind of wrote a sort of a Landgraph agent. What it essentially does is it kind of breaks down this hypothesis recursively. So in this example, the top, the top hypothesis was essentially broken down into 2 smaller child hypothesis. One being program has a high register count, or second, the program contains complex functions with many local variables, as an example, right? And it kind of kept on breaking this down recursively, almost like you can think of it as a chain of thought, but this is kind of more applied to hypothesis, though the same technique kind of applies. And you kind of keep breaking down these hypotheses into smaller hypotheses until you get to a stage where you say, enough, I don't need to break it down any further. Now I can actually gather evidence for these hypotheses based on the program. Now, it just kind of keeps breaking it down into a lot more, so this is just more of the same. But to kind of look at it from the point of a tree, you have a root hypothesis, you have all of these sub-hypotheses. These kind of keep get broken down into smaller ones. Ultimately, the leaves essentially represent the evidence for each of those hypotheses that you can actually gather to actually either validate or invalidate these sub-hypotheses. Now, what happens is, once you've kind of built the tree, you kind of start again from the bottom up, right? You start gathering all of these evidences. Now, what are these evidences and how are you going to gather them? Remember all of these structural analyses that we really kind of talked about? These evidences can essentially be gathered based on those structural analysis. Suppose we make a hypothesis of this is a complex loop. I'm just taking a very random example. One of the sub-hypotheses might be there is one node which essentially does dominate a bunch of other nodes, which would essentially validate the fact that that is actually a loop, for example. So each of these evidences can actually be gathered, and how these can be gathered, I think Chandru and I think the first talk also kind of talked about model context protocols tools, right? So all of these structural analysis that I had already kind of talked about, if say, for example, you essentially expose all of these pieces of functionality and analysis as MCP tools, right? And then you kind of run your hypothesis tree. Each of these evidences can essentially kind of activate each of these tools based on whichever tool is more appropriate for the kind of question that you're asking. And then, based on the presence or the absence of those evidences, you can essentially kind of aggregate up these beliefs all the way back up to the top of the root hypothesis, which will then change your belief in that root hypothesis from what it originally was into something which is called the posterior. Posterior basically means behind, which is like after in this case. So here is an example of running this sort of thing for that example that I kind of talked about. So initially, my belief in the hypothesis was 0.5. 0.5 in probability is like it's equally likely, right? Like it can be equally true or it can be equally false. After it had essentially kind of gathered out all the evidences and so on and so forth, the belief in the hypothesis kind of went down to 0.4. Now, 0.4 doesn't mean 0, right? I mean, you know, in this example, it's like purposefully ambiguous, but it kind of gives you a sense that our belief in this hypothesis has decreased. It hasn't gone down to 0. So it's not an all or nothing. Maybe there are other hypotheses that can even strengthen or weaken this hypothesis even further. But ultimately, whatever it is that we are asserting or whatever it is that you are asking an LLM to kind of give you is ultimately grounded on all the evidence that you're gathering based on deterministic information that is available in your legacy code, right? Which means that you always have a direct line of traceability from whatever it is that you are asserting down to the actual facts. You can be sure that it's not hallucinating, or at least you're minimizing the possibility of those sorts of things. This is just an example of like how I kind of built up the LangGraph agent itself. Like this is an example of how you have, when you start off an agent, it essentially builds up the hypothesis, and then you can see a cycle where it kind of like keeps decomposing the hypothesis in a recursive fashion. And then ultimately it kind of creates what I call an inference tree or like a hypothesis tree. And then this is the other loop which essentially kind of recursively kind of validates each of those sub-hypotheses, and then ultimately it kind of like updates the posterior, which is the thing that you kind of see at the bottom, and then ultimately that kind of aggregates back up all the way to the top of the root hypothesis. Now, one of the things that I kind of want to tie up is, yes, you're making hypotheses, but ultimately there has to be some plan. When you're faced with a massive legacy system, you can't just be like, start making like random hypotheses. You need to kind of have a plan, right? So, you know, what are the kinds of questions that you might want to ask a legacy system? You might want to know, you know what, these are the high-level, large-scale integrations of the system. These are the things that the system kind of talks to. Like these are all the different high-level system-level components, right? In that situation, do you kind of just give it the entire source code to kind of find out what the integrations are? No, right? In most cases, just say, for example, looking at configurations or just looking at, say, for example, like what calls are essentially being made, that is usually enough to know what sort of inter-system communication is happening. So why would you kind of dump source code, right? Why would you want to overload context? So in this example, suppose you want to know about the large-scale integrations, right? Like, you don't necessarily need to know the entire, give it the entire source code, right? Like, you can properly do context engineering based on, you can say, you know what, I want to be giving it the folder structure. I might want to be giving it like service and application configurations. I might want to be giving it documentation. In this way, what you end up doing is you kind of prevent overloading the context, right? You kind of give it exactly what is needed. You don't give it the entire source code and say, hey, figure out whatever it is that you can, and then kind of, like spray and pray and hope that it kind of gives you the final result, right? Conversely, suppose you wanted to know about the small scale structure of a particular program, not the entire context of the system. You would not really be interested in knowing the folder structure or something, right? You'd probably be more interested in knowing what are the method names, what sort of conditions are present, what sort of variable names are there, what sort of roles do those variables play. And each of these sorts of things, right? I mean, these plans can essentially be broken down, just like we kind of talked about using a hypothesis, the hypothesis, right, when we're validating it. You can use an LLM to say, hey, I want to make assertions about the small scale program purpose. I want to make assertions about the large scale integrations of a program. And depending upon that, instead of kind of dumping everything that you have about a program, it can intelligently kind of tell you, okay, you know what, I want to know only about these aspects of the program. And then each of these aspects of the program essentially use MCP servers, which expose all the deterministic analysis that I've kind of talked about, and I've covered only a thin slice of it. There's a lot more that you can essentially do. So think of this as more of a high-level overview of whether you're doing black box, whether you're doing white box or gray box or any other shades of gray, right? The idea is that not to kind of just give it context indiscriminately, but to be able to plan at the highest level to decide what is the kind of context that you need, and then leverage the appropriate tools that we have kind of already talked about, or other tools that you might come up with. And those are the tools which actually kind of give you the context, which you then use to ultimately, come up with a conclusion, which you then validate based on the sorts of hypothesis the hypothesis verification that I kind of talked about. Now, what does this mean at a high level, right? Like kind of tying all of these kind of together, right? Like, and I've listed only a few boxes. There can be a lot more boxes, but this is kind of just more of a increasing/decreasing levels of abstraction of what an infrastructure, a tool or a library or something that you are essentially building. There are different abstractions which kind of give you details give you facts at different levels of detail. So at the lowest level, you have, just be extracting out the structure, right? You want to be able to like extract out the structure. You want to parse. Maybe you want to like query the code and so on. On top of that, the structure itself doesn't actually give you answers. Now you need to kind of do some analysis on the structure. And at this point, you are still kind of mostly in the deterministic state, right? Like all the graph concepts that I kind of talked about and so on, as well as other techniques that, other talks might have even kind of talked about. Once you have all of this information, you can be sure that you have a stable, solid foundational base of facts which are incontrovertible. These are not in question because these are derived directly from the code base. Now you can essentially kind of start making hypotheses. You can start, exploring a whole bunch of possibilities. You can do a lot of exploration, but these explorations are essentially guided, validated/invalidated by the sorts of hypothesis proving framework kind of that I kind of talked about, right? Like creating the hypothesis and then reasoning about the hypothesis and then updating your world model based on whether that hypothesis is feasible or not. And then finally, obviously, you have the planner, which ultimately kind of tells you, what, do I want to know about the large scale structure of the system? Do I just want to know about this component? Or do I just want to know about a subset of the system itself, right? So, putting all of these things together essentially kind of gives you that sort of a deterministic foundation. So I'll just go back to the first thing of the benefits of the deterministic approach, and I apologize for kind of jumping around all over the place. But blah, blah, blah. Here. So benefits of the deterministic foundation, and this is something that I'll close with. Precision over speculation, right? Verifiable correctness. You always have a strong foundation on which to kind of base your hypothesis on. Scalable analysis, because you're not really depending upon the LLM for doing everything, which means that a lot of these things, because they're deterministic, they can be parallelized, they can be optimized, they can be run, like without having to worry about, like, am I hitting my context limit and so on and so forth. And finally, quantified confidence. Even if you are not completely certain of a hypothesis or some assertion that you're actually making, you can assign an actual number to it to kind of signal how confident you are. And not only can you hold one hypothesis, you can essentially hold conflicting hypotheses, each with its own varied degree level of confidence, right? Which can ultimately kind of make, in some sense, kind of make it a lot more trustworthy, because you're not like blindly being led down one path where, which is kind of like given by the LLM.